Okay, good morning, good afternoon, whenever you're tuning in. This is 8.01 and 8.02 wrapped together. A highlight of some key concepts so far. Our objective at the end of this will be able to explain the role of the derivative and use proper, I should say, notation to interpret the derivative. And then we're going to use the limit definition of the derivative to find the slope of a tangent line at a given point. This is what we're reviewing: derivative, slope, tangent line. Let's dive in. The first thing that you have to know, and this was 8.01, was the difference between a tangent line and a secant line. And these are two definitions that we have to become very familiar with and know how to find the slopes of each one of those. So you'll notice here that with a secant line, we have a line that intersects a curve at 2 points, whereas a tangent line, we have a line that intersects a curve at 1 point. So right there, there's a huge difference. And how we find the slope of those two things, or how the slopes relate, is that the secant line is really the slope is the average rate of change. Right? We know that formula, and that formula for average rate of change would be y2 minus y1 over x2 minus x1, right? Or we could just call that change in y over change in x, delta y over delta x. Okay, but what's different about a tangent line is that we can't use the slope the same way because there's only 1 point. How do I use change in y over change in x if there's only 1 point? So the tangent line is nice because it tells us the instantaneous rate of change, the rate of change at a given instant. So some pictures of those, if we were to take maybe some quadratics with an a term that was negative here in each one of these, we'll draw a picture for each one of these. A tangent line would be any 2 points, or sorry, a secant line would be any 2 points connected, intersecting right there. There's my secant line. Whereas a tangent line not only intersects once, but it has the same slope at that point. So notice how that graph is kind of increasing there and it starts to kind of increase a little bit slower. Our graph has to kind of match that. So if I zoomed in, that would be linear. Our tangent line is just going to barely touch it and keep going. And at that point, they're going to have the same slope. The line and the curve are both kind of going at the same rate. So this would be my tangent. So notice two things here. What some students in class were saying is that, oh yeah, a secant has 2 points where a tangent line has 1. It's more than that. Remember that secant also is average rate of change, where tangent is instantaneous rate of change. Now this brings up a lot of problems. Like with secant, we can very easily have a formula for finding the average rate of change. But how do I do that for tangent? Once again, we need 2 points and we only have 1. So that's what we're going to dive into today and talk about how can I find the slope of a tangent line? What is my strategy and method going to be? So make sure this is in your notes. Let's move on and find that. Here's an example. We're going to find the slope of f of x. It's listed here. And f of x is 2 radical x. Okay, I've graphed it for you. And we're going to find the slope at x equals 1. Maybe thinking, well, how do I find the slope at a given point? There's only 1 point there, right? We can see it right there. There's only 1 point. So how do I find the slope? How do I find change in y over change in x? There's only 1 point. Well, we can kind of see that at that point, we have a general slope here. So we can sketch it and kind of see, what would that be at that point and kind of estimate it. But if I'm finding the slope at 1 point, clearly we're talking about finding the slope of the tangent line, right? There's an issue, right? We only have 1 point. So how do I find this tangent line? How do I do something like that? Well, what we're actually going to do to start is we're going to start by doing some secant slopes, some secant lines. So we can see that that same curve, I'm going to actually connect 2 points, one from 1 to 9. So there's my interval from 1 to 9. Those are the x values. And I'm going to find my rise over my run, my rate of change, which is 1/2. So my slope of this secant line, right, this secant line, my slope is 0.5. And remember, we're looking for the slope here, just at that point. So that tells us the slope between 2 points, but not at 1 point. And what we're going to do here is we're going to show how if we make those points a little bit closer, instead of between 1 and 9, we make them between 1 and 4, our slope changes. And instead of going from 1 to 4, we go from 1 to 3. We make those 2 points even closer together. Our slope changes. And we notice that we started with a secant line that is slowly creeping closer together. These 2 points are getting closer together. And as we bring those points closer together, it starts to resemble a tangent line. So here's between 1 and 2. And between 1 and 1.5, we can see how the slope is changing. And between 1 and 1.1, now those dots are very, very close. Notice how, even though we still have 2 points, look at how much that resembles a tangent line. And we can even go closer. 1 and 1.01. Now those are so close you can't even tell the difference. Now there are 2 points there. And we can see how this is our best approximation for a tangent line. So let me just write that in. This so far is our best approximation for tangent. Okay, and the computer's actually found the slope already. So this tangent line right here has a slope of 0.9975. So we can see that as those points got closer together, right, the slope changed from 0.5 to 0.667 to 0.723. It's increasing, 0.8284, 0.8999, 0.9762, 0.9975, right? So that slope is changing and is kind of zeroing in and getting closer and closer to what that tangent slope would be. So here's a list of all those values written out for you. And we highlighted the fact that this last one, between 1.01 and 1.1, which is just 0.01 apart, has the best approximation for our tangent line. So we could say, okay, remember what our goal was. Our goal was to find what is the slope at that single point. Well, it's going to be somewhere around 9975, but let's think about this. If you were to think about going one step further and trying to get these points even closer, you could even choose points like 1.000000001. Some points that are even closer than 1 and 1.01, right? Where our distance would be super, super small. Okay, and we would see that this would kind of really start to increase and get really, really close to 1 whole. So we're approximating and we're approaching the slope at a single point. So as these get closer, so as change in x decreases, right, which basically just tells us that our points are getting closer together, we see that our slope increases, but it doesn't increase to infinity. It increases, or approaches, I should say, instead of increases. It approaches our tangent slope. So it approaches slope at exactly x equals 1, which in this case also turns out to be 1 whole. Now that won't always match up like that, where it's 1 and 1. Yeah, our slope could have been anything there, depending on the graph. So what do I want you to know? Secant lines can be used to find the tangent line or approximate it if those secant lines have points that are very close together. So this would be my approximation method. I would say something along the lines of, as our distance between our x values decreases, our slope approaches the slope of the tangent line. So we're using secants to approximate tangent. Okay, so where does that leave us? Now what do we do with that information? Well, we're going to use it in a second to find the derivative. So right now we know tangent lines, secant lines, and we know how we can use secants to find tangents. And we're going to put that all together with this new vocabulary word, the derivative. You're going to write this down. The derivative is a mathematical operation, so to speak, that tells us the slope of the tangent line at a given point. Okay, and some annotations that I would put in here. One annotation would be slope of tangent line. I could also put as instant rate of change, right? Instantaneous rate of change. Okay, and we know that this is tangent line because there's going to be 1 point given. So I won't be doing secant because I won't have 2 points. I'll only have one single given point. So the derivative allows us to do that process that we were just talking about, where we close down those secant values into a tangent line. We need to know the notation of the derivative. So there are several ways to write derivative. So if I have something like this, f of x is my original function, we can change that to f prime of x, and this would be the derivative. Okay. And we call that, once again, f prime is how we would say that. We could also use like y and y prime. Y prime would talk about the derivative of y. Other ways to write this would be, instead of y, we could write dy d over dx, which we just call dy dx. That's another way to talk about the derivative. And if we had f of x, we could also use the derivative d dx over, of f of x. So all of these things are used to annotate and signify that I'm taking the derivative. So we are going to have an original function, and then we're going to try to find the derivative of that. And we're going to have to interpret that. So we need to know these things, and that these things tell us the derivative, and that the derivative tells us the slope of a tangent line. We have to piece those pieces of information together, put them together when we're given a particular prompt. Let's talk about this. What does, so let's just kind of clear this, and I'll talk about the next thing. What is f prime of, or sorry, what, yeah, let's make this f prime of -2. What does that tell us? F prime of -2 tells us what? Well, I can look back to the last page of our notes, and I would say that tells us the slope of the tangent line. I can use that. So what we need to do is be able to, see something like this today and know, what does it mean? It tells us to find the slope of the line tangent to f of x at x equals -2. That's one way to interpret this. If you want to take that a step further, it tells us to find the instantaneous rate of change I'm going to put ROC for rate of change. Find the instantaneous rate of change of f of x, whatever that function is, at x equals -2. So we know that since they're only giving us 1 point, we must be talking about one of two things. We must be talking about the slope of the tangent line, or we must be talking about a synonym, the instantaneous rate of change. So that f prime tells us that we're talking about tangent, or that we're talking about instantaneous rate of change at a given point. All right, so we can use secants to kind of help us do that. And we've got another method for doing that as well, which we'll discuss, like how we'll actually do this. But right now I want you to understand that that's the relationship. Now, let's just talk about some questions that you would have to answer. For the following, we'll be using the function f of x equals x squared minus 2x plus 1. What's the difference between f of 2 and f prime of 2? What's the difference between f of 2 and f prime of 2? Well, f of 2 tells us the output, the y value of f of x at x equals 2. And then whereas f prime of 2, remember that tells us the derivative, right? I'm not just going to say f prime of 2 is the derivative. What does it tell us? it tells us, I've got an S in there, tells us the what? The slope, the average rate of change, the slope of the tangent line at x equals 2 of f of x, right, of that function. In addition, what I could have put in there as well is instantaneous rate of change of f of x at x equals 2, right? So there's a difference here. One of them tells us, just clearly we put that in, we get a point, right? We'll kind of know a point on our graph. Where another one, if we actually take the derivative, it tells us the slope at a point. And that's the difference between these two notations here, specifically this new notation that we're talking about. Okay, so let's talk about one, like how would I find that given a graph? Like what if I were we're going to find f prime of 3. What does that tell me? It tells me derivative, right? At x equals 3. Well, what does that tell me? That I need the slope, right? At a given point, at x equals 3. How do I find the slope? Well, I need the tangent line. I'm already given the tangent line. So all of these pieces of information need to be related together. Here's my tangent line. There's my red one, right? You can see my f function right here, right? This is my function f of x. So if I'm looking for the slope at x equals 3, here's 3. What's the slope there? Well, what's the slope of my tangent line? Let's actually count it. The slope of that tangent line is down to over 1. So therefore, what is f prime of 3? F prime of 3 is equal to -2. And once again, why? Because that's the slope of the tangent line at that point. So if I have a tangent line, I need the slope, I'm taking derivative. All of those things being related together.